All right, guys, here's lesson 9.1 called differential equations. Essentially, a differential equation is one that has x's and y's can be on both sides of the equal sign, and there also can be first and possibly second derivatives within the differential equation. Our job is to solve for y in the long run and get back to what is considered the original equation. Sometimes an initial value will be given, and therefore we can find what's called a particular solution. Other times there's not, and we would find a general solution would be the use of the constant c, as we've seen before. Okay. So on the left-hand column there, differential equations could look like those, and on the right-hand side, general solutions would look like y equals equations. We're going to go through a couple examples early on that are relevant in terms of classifying, but you won't really see these types of questions on the AP exam. So you can see that the first differential equation there in the list, x squared times y prime plus e to the xy equals 4. This is considered a first order because the y terms, which is what we look at, has a first derivative, and it's considered linear, again, because the y terms don't have any exponents on them. Second one's first order because y is just the first derivative again, but this time y prime is being squared, so it is nonlinear. Third one, second order. This is because we have a second derivative, but now the y terms are all linear. They don't have exponents on them. And then we have a third order, and we have nonlinear because y is inside of sine. Okay. So those are just for classifying purposes, not super relevant. Don't worry about having that all memorized. Okay. I'll leave these practice problems for you. Go ahead and pause it if you want to give it a try, and then I'll fill in the answers for you. Okay. Okay, here's another type of problem that we start this section off with, but it's not the way the AP or even I will ask you these questions moving forward. This is more of the verifying to make sure that we do have a differential matched with its corresponding solution or original equation. Okay, so it's sort of like, I guess I would relate this type of question when we were given inverse relationships in Algebra 2 and you were asked to confirm are these f and g actually inverse functions or not. So similar idea here. Again, it's not the format that you'll see moving forward though. So the first thing you're going to do is solve for each of the derivatives needed. So what that means is if we look at the differential on the left-hand side, we need a y prime. Okay, so we take the right equation and we derive it so that we get our y prime. So y prime is equal to 1/2, right, this is chain rule, 12 minus 4x squared to the negative 1/2 power, multiplied by inner prime of negative 8x. I can simplify this and write it as negative 4x divided by square root of 12 minus 4x squared. So we're going to take that and we're going to substitute it into what is considered the original. It's considered the original because that's what you would start off with. You would start off with a differential and you would work with that. So we call it the original, and y prime gets replaced with the negative 4x over square root 12 minus 4x squared. Y also gets replaced with square root 12 minus 4x squared. So we're substituting in values of y and y prime. the 4x stays, and the 0 stays. And now once we've substituted, we can look to simplify and solve it. And you can see that your square roots cancel. You're left with negative 4x plus 4x equals 0. And of course, that is a true statement, which confirms that we did begin with a differential and the general solution, or the original and the solution. Okay, so let's move into problems that would be giving us a differential, and we would look to solve them. Now, because of the nature of a differential equation where x's and y's, y prime, y double prime, y triple prime could all be within the same equation, you might be thinking of, wow, these problems could get really, really complicated. Well, yes and no. First of all, not every differentiable is separable, so therefore we cannot solve it. Okay, so when solving for a general solution, the first step will be to determine whether the equation is separable or not. So we want to figure out, can we put the y's on one side and the x's on the other side? So if we have dy over dx equals sine x times y, I like that it's written as dy over dx rather than y prime, because that allows us to begin to separate, including the dy and the dx terms. Okay. So in this case, I can divide by y, and that would put dy over y, and I can multiply by dx, and that would give me sine x dx. So at this stage, all I'm doing is confirming that it's separable. The second one, dy over dx equals x plus y, because of the nature of addition and subtraction, those are the ones that can be more complicated and potentially non-separable. So I could start by maybe subtracting y, and then I would maybe multiply by dx, but ultimately I'm always going to be multiplying a quantity, and there will be no way in this case to factor out or totally separate the x's from the y's. And in the the third one, I would first want to write y prime as dy over dx. Yes, I do have an x squared and an e to the negative y equals 0. It helps that this is equal to 0. I don't have a third term that's complicating things. So now I could move the e to the negative y over first. So I turn it into two terms. I could divide by the x squared. And then it would be multiply by dx, divide by e to the negative y. So that might not be the format that I wanted in, but nonetheless it's separated. Okay. So your first job when you're looking at these is figure out, can you separate or not? Okay, so this one we talked about already. Moving on. Sorry guys, I squeezed all this work onto the one page I didn't realize I had separate. Okay, so here's our first example. And these instructions now say solve the differential equation. So I'm going to write these steps in terms of the process in 3 words that are pretty easy to remember. First is separate, meaning put all x's on one side and y's on the other. Once you have that, including your dy and your dx, then you're going to integrate. These are indefinite integrals, so you're going to add c to the x side only. And we'll talk about that in a minute. And finally, you're going to solve for y. So the three words that I would want you to focus on here would be separate, integrate, and solve for y. Okay, so here's our first equation. All right. So I'm going to add x. And then I'm going to multiply by dx. So I have completed the separate step, and now I'm going to integrate. And I integrate both sides independent of one another. So you can see that I just inserted an integral symbol on both sides. So now I am doing reverse power rule. So y squared divided by 2 equals x squared divided by 2 plus c. Okay, so here's why you only want to add c to the x side. If I were to add it to both sides of the equation at this time, right, plus c, all of us automatically would say, oh, well, the c's just cancel out. But that's not true, right? The c is some unknown value. We don't know what it is. The c on the left is most likely different than the c on the right. And therefore, I just want to account that I have some kind of constant. I still have no idea. So the only time you want to show an operation on a c is when it is essentially cumulative, when it impacts, because of order of operations, your result. So you'll see that happen in this problem. So I've integrated, and now my final step is to solve for y. So I'm going to multiply by 2. So in this case, I can distribute my 2, quote unquote, and that just becomes an x squared. And here's an example where I don't have to write 2c. 2c is still some unknown c value. If you write 2c, that is fine. But if you're going to choose to do that, be consistent with it and be careful, because later on when we solve for our c's, your c, at the very, very end of the problem, the result will be the same, but during the solving process, it will look different. Okay. And now finally, when I take the square root, I do need a plus and minus. This is where the c has to be under the square root, right? It's part of a quantity. It wouldn't have mattered if it was a 2c or a regular c, but it is under the square root. Okay. And that would be our answer. That's our general solution to the differential equation. Okay, so let's look at a couple more. Okay, in this example, it starts off as y prime equals x times secant y. Always rewrite y primes as dy over x's. Remember, they're equivalent. It's just a different way of notating it. Okay, we need to be able to separate that y prime concept. Okay. Okay. Remember, the secant has y inside of it, so therefore the secant and the y will always stay together. The x with the secant is multiplication. So I'm going to multiply by dx, and I'm going to divide by secant y. If I have a 1 over a secant, I really have a cosine. So cosine y dy equals x dx. Separated, I've written it as neatly as I can, and now I can integrate it. So the integral of cosine y becomes sine y, and x becomes x squared divided by 2 plus c. Final step, isolate my y. In order to undo a sign, I need a sine inverse. So y is equal to sine inverse of the entire quantity, x squared over 2 plus c. Okay. Take a break. All right, next example. ln y times y prime minus ty. So you can try this on your own, pause it, work on it, or follow along with me. This one will require a u sub when we are integrating, so it gets a little bit trickier. Let's see what happens. Again, take that y prime and rewrite it. Notice that the second variable in this equation is a t. If you don't like that, change it to an x, but I'm writing y prime as dy over dt. Okay, so I'm going to add ty to the other side for now. I'm going to multiply by dt and divide by y. Okay. So here's where we're ready to integrate, but the left-hand side is a little tricky looking. Okay, and this is not a traditional u sub, because a lot of the times I've said use the denominator as your u. In this case, I end up using ln y as my u, because ln y derives to 1 over y. If I use y as my u, my denominator, y will not derive to ln y, which is what I would need. So it's okay to pick the incorrect thing in the beginning, but again, you need to find all of those pieces. So the only way to complete my substitution would be to start with ln y being my u. du is then 1 over y dy. So that completes everything I need in order to rewrite this u sub. So now I just have the integral of u du equals the integral of t dt. So u squared over 2 equals t squared over 2 plus c. ln y goes back in for u. And I'm going to solve for my y. You might find that you wait until the end to put the u back in. That's up to you. Okay, you don't have to substitute immediately. So I'm going to multiply by 2. So that is one of the things where the 2 does cancel out the 1/2 on the t squared. You can put it as a 2c or not. That's okay. Then I'm going to square root. Plus or minus. C must be underneath of the square root. And then I'm going to exponentiate. In order to undo an ln, I would have to raise the whole thing to the e with a base e. So y is equal to e to the plus or minus square root of t squared plus c. All right, the last couple of examples are considered initial value problems where we're looking for a particular solution. So you'll have that ordered pair relationship that you'll use at the end. That's what's going to allow us to solve for C. So y prime is dy over dt here. We get y dy equals negative t dt. I'm sorry, we don't get y dy, we get dy over y. Okay, so now when we integrate, we're integrating a 1 over y, which goes to ln absolute value of y equals negative t squared over 2 plus c. We exponentiate, and we get the absolute value of y equals e to the negative t squared over 2 plus c. We don't need the absolute value on the y in this case. It's not wrong to keep it, but an exponential is always going to be positive in this case, so we don't have to worry about that. Then we use our initial condition to figure out what c is equal to. So 3 equals e to the 0 plus c. So then if we apply an ln to both sides, we get ln of 3 equals 0 plus c, or c. So plugging that back in, y equals e to the negative t squared divided by 2 plus ln 3. So this is where we talked about properties of logs can be the game changer in a 4 to a 5 on the AP. Using properties of logs here to fully simplify this and get the correct answer will get you more points in an open-ended or the correct answer on a multiple choice. And I'm going to show you in another example, you can solve for C at a different location, right? I could solve for C as soon as I've integrated, and that might make this process even easier. But for now, I've got myself in this place where I know I'm not fully simplified because I have an ln in the exponent of an exponential. So the first thing I'm going to use, properties of exponents. If I have addition in my exponent, that means I must have had same bases separated with multiplication. And now if I have e to the ln 3, well, that's just 3. So I can write that as a coefficient. And now I'm done. Okay, 2 more examples in these notes. And then I highly recommend doing practice problems. Okay, so I separated. I acknowledged that I had a negative exponent in the denominator, so before integrating, I bumped that up and it became a positive. So e to the y equals t squared over 2 plus c, and y equals ln of t squared over 2 plus c. I have the relationship of 1 comma 0. So in this case, I replace the y with 0, replace the t with 1. In order to solve for c, I'm going to exponentiate. So I have e and e on both sides. E to the 0 is 1. E to the ln is an inverse, so that cancels out. So then I have 1 equals a half plus c, and c equals a half. So y is equal to ln of t squared over 2 plus a half, leave it like that, or t squared plus 1, all divided by 2 inside your ln. Okay, final example for today. Pause it if you want to try this on your own, and then come back. Okay, so I'm separated, and here's where I do need to use a u sub. My denominator is 3y minus 12. My du is 3 dy. So 1/3 du is dy. So I have a 1/3 1/u du. Integral dx.
Yeah.
Right. So integrating this, I have 1/3
What?
ln u equals
Check.
x plus c. So 1/3 ln of 3y minus 12 is equal to x plus c, multiplied by 3, exponentiate, acknowledge, because of that original example, that anytime you have this constant up there, the shortcut is you can always pull it down as a c e to the 3x. Because ultimately, it's addition, and it's like saying e to the 3x times e to the c. I'm sorry, times times e to the c. And then when we apply an ln, it ends up just becoming the constant. Okay. So here I'm going to add 12 and divide by 3. And when I do that, remember c over 3 is still just c. So I have c e to the 3x plus 4. I plug in my information, 2, 1. And I solve. So final answer, using my c, goes back into there. This could also be rewritten as -3 e. I'm dividing with the same base, so I can show that with subtraction in my exponent. Plus 4. Okay. All right, so that's it. Homework is there. It'll be posted on the website, and there will be a worksheet or packet included as well. You don't have to do every single problem in the packet that I post, but do enough to feel like you understand what's going on.